Okay, sorry about that. Seemed like I have trouble there. All right, so we're going to continue on here. I think my computer just had a heart attack there, so hopefully it's back. All of a sudden, it just like shut down, I think. So, all right, so we're in the middle of this problem here. Thank you for coming back. Let's see where we were. Of course, when it just crashed there, it did not save anything. So, previously, we used again our boiling point there equation to figure out the actual change in boiling point temperature, which again was our 105 minus our 100, which got us to 5 degrees Celsius. We then used that and the equation there to solve for the molality, which would give us our change in boiling point temperature divided by our KB, which was for water, which was again our 5 degrees Celsius divided by our 0.12 degrees Celsius. And I believe that was 9 point something, if I'm not mistaken, 9.77 molality, which again was 9.77 moles per kilogram. So remember, ultimately, we want to get to grams. So we do want to get to moles, basically. So that's where we're going to use our solvent, which was the 1 kilogram of water, right? That was our solvent. And we're basically going to times that by the molality. And the kilogram of solvent will cancel out, and that will get us a 9.77 moles of our solute, which is the C2H6O2 in this case. So now that we got to moles, what we have left is to get ourselves to grams, and they were nice enough to give us that number right here. Again, if they weren't or did not give us that number, we would go to the periodic table and get the molar mass. So the molar mass here is going to allow us to convert to grams. We're going to multiply by the molar mass, which looks like 6207 grams per mole. Moles are going to cancel, and that's going to get us, I think, what you had up there. So about 606, if you will, grams. Would be dissolved in this solution. Any questions on that particular one there? Okay. Let us continue while we still have things working, I guess. So here's the same problem, neatly done, I guess. Scroll it up there in case you want to look at it later. All right, so why don't you try this one here and see what you come up with. We want to calculate the actual boiling point of a solution that's made by dissolving 1 gram of glycerin, C3H8O3, in 54 grams of water. And they were nice enough to give you the molar mass there as well, which again, if you were not given, you would find on the periodic table. So why don't you take a couple of moments here and see what you come up with, and then I'll double check, make sure we get the same answer. All right, so let's take a look here and see how we're doing. So we're looking for the boiling point. So again, we want to make sure that we are using the boiling point formula there. So in this case, we're not given the molality, but we do have enough information to figure it out. We have the grams of the solute. We do have the kilograms of the solvent, which is what this would be. So we would want to calculate the molality here, and the Kb is obviously a constant. So again, it's the boiling point constant, and it is for water. So that's again from a table where we would get that information. So we'll start with the molality. So in order to do that, that is moles over kilogram of solvent. So to get the moles, we want to take the 1 gram of glycerin. And again, they were nice enough to give us the molar mass, but if not, you would have to go to the periodic table and calculate that. And that looks like it will get us 1 divided by 9209. 0.01086 moles. We also see that this is our solvent, but remember that molality is kilograms of solvent. So we do want to take the 54 grams and basically convert it into kilograms. You divide by 1,000 or move the decimal point, whichever way you want to do it. And that will give you 0.054 kilograms, which means our molality would be 0.201. And again, you can leave it as little m. You could leave it in moles per kilogram if you like. So now that we have the molality and obviously we have the Kb, if we put them in there together, 0.201 molality, our Kb at 0.512. Molalities are going to cancel, and that will get us 0.103, we'll call it. And again, a reminder here that that is not the answer. That is, again, the change in the boiling point temperature. So we do need to use that relationship. Again, since this is elevation, the solution will be larger number than the solvent. So we will take, in this case, the temperature of the solution minus temperature of the solvent, which means the temperature of the solution would equal the change in the boiling point temperature plus the temperature of our solvent where it normally boils. And that's going to give us 0.103 plus 100 degrees Celsius. And that will give us a boiling point for this solution of 100.1 degrees Celsius. It went up a little bit, not tremendous, but it did go up a smidge from where water would normally boil, which would be 100 degrees Celsius. Any questions on that calculation? And again, this is the same one, just with it all printed. Got the same answer, so that's good. All right, so another sort of colligative property we're going to look at is osmotic pressure. And the osmotic pressure is basically the pressure that's needed to keep a liquid level on both sides of a membrane. So sort of the idea here is osmosis. And osmosis, for example, if you had a container or a column, if you will, where you had a membrane in between. And on one side, let's just say you had salt water. And on the other side of the membrane, you had just pure water. Right? And basically what osmosis basically is the passage of from a lower concentration, which is what the little brackets mean, to an area of higher concentration. So in this situation, what's going to happen is the solvent water molecules on this side, which is lower concentration, is going to flow over to the other side where there's salt and particles basically dissolved in it, in sort of an effort to dilute the other side and dilute it down. And it will continue to flow until it pretty much hits a point that is equal to kind of the atmospheric pressure pushing down on it. And that is basically what is known as the osmotic pressure. So because the osmotic pressure basically is pushing back the other way, it is stopping the continual flow of water molecules from one side to the next through the sort of natural process of osmosis, which is where we go from lower concentration to higher concentration. You could actually calculate the osmotic pressure, which is sometimes abbreviated with this little symbol. And we'll talk about this here in just a sec, but really what all this is your ideal gas law, your PV equals nRT. And if you divide V to the other side, you get P is equal to nRT divided by V. And if we look at these two units when we're in the ideal gas law, N is moles and L is liters, and that is molarity, which is what this is. Yeah. And that leaves us just the RT. So that is how we get to molarity times RT, which is R is our same gas constant that we use with the ideal gas law. And obviously T here is temperature in Kelvin, and P, because really this is the ideal gas law, is also needs to be in atmospheres. So it's really the ideal gas law. Sometimes they'll just kind of use a different symbol and they'll kind of apply it to what is known as osmotic pressure. But it's basically a ideal gas law problem. What reverse osmosis is, right, is basically they apply a pressure greater than the atmospheric pressure, and that basically pushes everything back sort of the other way. When you do sort of reverse osmosis, you apply that greater pressure, and it pushes all that water molecules back the other way. And usually you'll have a lot of filters here to catch all the other stuff you don't want going through, and you get kind of pure-ish water. So let's take a look at a problem here. So we want to know what is the molar mass of a protein if 5.87 milligrams per 10 milliliters gives an osmotic pressure of 2.45 torr and 25 degrees Celsius. So again, since we're thinking about osmotic pressure, you really could just think about PV equals nRT if you like. That's our P, that's our T, and that is our V in this case. And here is really our moles in that particular case. So we're looking for molar mass, which again is grams per mole. So we have P, we have T, we have V. We have everything we need to use the ideal gas law basically to solve for N. And if we solve for N, N is equal to PV divided by RT. Again, dividing this to this side. But really, again, because everybody here is in the ideal gas law, we do need to do some conversions. So we need to take 2.45 torr, and we need to divide it by 760 to convert it into atmospheres. And if we do that, 0.00322 atmospheres. We obviously need to convert our temperature into Kelvin. So we're going to add 273 to that guy. Going to get us to 298 Kelvin. And in this case, we're going to take our milliliters and convert it to liters. So we're going to divide by 1,000.01 liters. So if we put all those numbers in here, that's 0.00322 atmospheres. Our volume 0.01 liters divided by R, which is the same one we use for the ideal gas law. and our temperature, which is 298 Kelvin. And if we do all that good stuff there, we get some moles here. That is 1.32 times 10 to the minus 6 moles. This is our grams up here. We need to convert it to grams, so 5.87 milligrams. There's 1,000 milligrams in a gram. So again, divided by 1,000 or move the decimal. That will give us 5.87 times 10 to the minus 3 grams. So now we have the grams, we have the moles. So putting it together, the molar mass would equal 5.87 times 10 to the minus 3 grams divided by 1.32 times 10 to the minus 6 moles. And that will get us a molar mass of 4.5, we'll call it, times 10 to the 3 grams per mole. And it is a protein, so it would probably be a relatively large molar mass, as it probably has a lot of things in there, about 4,400 grams per mole. Question on this. So this is kind of similar to what we did with the ideal gas law when we were talking about calculating density and calculating molar mass using the ideal gas law. So it's essentially kind of the same equation that we saw when we were dealing with gases. Any questions on that? Okay. Let's get this one here. It's kind of the same question, basically. So up until this point, when we're talking about colligative properties, we've really dealt with non-ionic solutes. And the deal with non-ionic solutes is when it goes for a swim, when you're a non-ionic or covalent, when you put that guy into water, for example, you pretty much get that guy. He's just dissolved. So you basically get one particle. But that does change if you try to dissolve an ionic compound in water. So if we take something like sodium chloride and we put it in water, we actually get a sodium ion and a chloride ion. We get actually two particles that go into that water. And because all of this stuff is basically based on the number of particles as to how it affects boiling point and freezing point and such, when we are dissolving something that is ionic, that will break apart into more than one particle, we do have to take that into account. And that is what is sometimes referred to as the von Hoff factor, this I. And essentially, when we take our freezing point formulas or our boiling point formulas, which is the one we saw here earlier, we actually need to add the I into the formula, and it's not too bad. You essentially just add the I there. So in an ionic compound, when you do boiling point or freezing point, an ionic solute, you do need to use these formulas, unlike the ones that we used earlier. The good news is it works the same way. The only additional thing that you have to do is basically include the I as sort of a factor, because you get more particles when you have an ionic compound that goes into solution. So how do you figure out I? It's pretty simple. Sodium chloride breaks apart into two ions, which means for sodium chloride, I would equal 2. If you had something like calcium chloride, it would break apart into a calcium ion plus 2 chloride ions. That's a grand total of 3. which means for calcium chloride, I would equal 3. So again, you basically just need to kind of incorporate I into the calculation when you're dealing with ionic solutes in freezing point, boiling point, also vapor pressure lowering as well. You would put the I in there. You would also include it with that calculation as well. Now, most of the time, we will just use the expected value for I, which you could get from the formula breaking apart. So for example, here, iron 3 chloride, you get 1 iron 3, and 3 chloride ions, I would equal 4. In reality, though, experimentally, they are slightly different than those numbers. So you can see here, sodium chloride, you actually get 1.9 when you do it. Magnesium sulfate, you actually get 1.3 experimentally, 2.7 for this guy. So experimentally, the I values when they're calculated are really slightly different than what would be predicted based off of the formula. But for calculations that you do, you pretty much could just base it off the formula. And that's why for non-electrolytes, which is essentially what we were talking about earlier, that basically are guys that don't produce ions, they stay together, but they do dissolve. These non-electrolytes, basically, as you can see there, the I value is equal to 1. So when we look at those formulas that we were using earlier, if we did I is M times KF, I would equal 1, which gets us to the equations we were using earlier. So we just kind of assumed that I was 1 with those non-electrolytes. Again, a reminder, non-electrolytes will dissolve in solution, but not produce any ions. And again, that's why I is equal to 1. So when you're dealing with something ionic, you want to make sure that you include the I in those formulas, especially the boiling point and freezing point formula. Any questions on that? Now we could actually calculate the von Hoff factor using some of that information. So in this particular problem here, they say they want to know what is the von Hoff factor if we have a 0.05 molality solution of calcium chloride, and it has a freezing point of minus 0.27. So again, here we would use our freezing point formula, but we would include the I here. And that is because the solute we're dealing with is ionic. Now, in this particular case, we're actually looking for I. So if we rearrange this, I would equal the change in the freezing point divided by MKF. KF is going to be that 1.86 number because, again, waters are solvent here. M is our molality, which they gave us. And the change in freezing point, again, is not going to be this number because the change in freezing point is the temperature of the solvent where it freezes minus the temperature of the solution. So water freezes at 0 degrees Celsius minus the solution, which is minus 0.27 degrees Celsius. Again, this is how we get rid of the negative sign. And now we can figure out I would be 0.27 degrees Celsius divided by our molality 0.05 divided by our KF, which is 1.86 degrees Celsius over molality. And if we do all that good stuff there, we get something like an I value of 2.9 for the von Hoff factor for calcium chloride in this particular solution, right? And that's not bad if you were to guess just using the formula like we saw earlier. This again breaks apart into calcium plus 2 chlorides. That's a grand total of 3 ions, which you would assume I would be 3, which again is fairly close to sort of the experimental value that you would get when you calculate I. So you could do all these freezing point, boiling point guys. Again, if you do it for a non-electrolyte, which does not break apart into ions, you don't have to worry about I. But if you do it for some type of ionic compound that does break apart into ions, you do have to worry about I, and obviously include it in the calculation. Any questions on boiling point, freezing point, osmotic pressure, how to do any of those calculations? Obviously, you do need to know how to do those. All right, so let's finish up just talking about some last little bit of properties of solution here. So we sort of touched a little bit about the semi-pyramidal membrane when we were talking about osmosis, but a membrane is basically something that allows certain size molecules to float through. Like in our body, we have lipid membranes and all those kind of stuff. But basically, sort of the simplified version of it is a membrane kind of has holes in it, if you want to think about it. And these holes basically are small enough to let certain things pass through. But, you know, if you got something that's kind of on the large side, it's not going to fit through. It's not going to be able to pass through. So it can act sort of as a filter, if you want to think about it that way, allowing certain size guys to go through, but other size ones not able to pass through. Now we have certain types of solutions, if you will, or particles. And colloids are much larger than solute particles in solution. These are really large molecules like proteins and groups of molecules or ions. They are homogeneous mixtures, which means they look the same throughout. They do not separate or settle out, but colloids are small enough to go through filters like filter paper. If you put a filter paper on like a funnel, it will go through, but they're too large, for example, to go through like the membrane that we have drawn up there on the screen. Now we also have suspensions. Suspensions are heterogeneous mixtures. And that basically means that you see different phases or different parts to it. And these are really large that you can kind of see it with your naked eye. And these are so large that they pretty much get trapped by filters. They get trapped by membranes. They pretty much aren't going anywhere. They're just too big and you can kind of see them. So for example, if you had water and you threw some salt in there and you threw some sand in there with it and you mixed it all together, when you would go to filter the salt water and the sand would get caught on the filter paper, right? It wouldn't go through. It's a suspension in that example. It obviously wouldn't be able to go through the filter paper, but the salt in the solution is small enough to pass through the filter paper. And so again, suspensions are really large sort of guys that you could basically see and get trapped. Here's kind of a zoomed in. Again, here our membrane. Again, it has sort of channels, if you want to think about it, that again allows certain size guys to get through. But again, these really big molecules over here get trapped because they can't really get through the size or the openings. So here's just an example. Our suspensions settle. Solution of colloids will kind of float around. If you go to filter it, you can see that the solution in colloid will go through the filter paper, but again, those really large guys, those suspensions get caught in it. And this is something like a dialysis bag or sort of a membrane, again, allowing solution molecules of small size basically to flow in and out. So we sort of talked about osmosis, but again, just a reminder, osmosis, again, is really the flow of water molecules or solvent molecules from an area of lower concentration to an area of higher concentration. Again, kind of in the idea of it trying to dilute down the more concentrated area and sort of equalize sort of the concentrations on both sides of a membrane. And as we talked about the osmotic pressure, which you could calculate using really the ideal gas law, is basically the pressure that comes down as those water molecules, for example, are flowing to the other side, and at some point will prevent the further flow of the water molecules from the lower concentration to the higher concentration. Now, the greater number of particles that you have dissolved in a solution, the greater the osmotic pressure you would have. And that's why something like pure water, for example, has no osmotic pressure. So if you have pure water, you pretty much have just H2O in there. You have no particles floating around, and no particles are floating around. Come back. Thank you. And they would have no osmotic pressure in that particular case. So here's just an example that on one side you have water, you have your membrane in between, and over here is a brine solution, which is basically a very heavy salted type solution. So obviously the brine solution is much more concentrated than the water. So by the natural flow of osmosis, this water molecules, which is less concentrated, is going to head over to the other side again in an attempt to sort of dilute it down. And at some point, that flow of water molecules will be stopped by the atmospheric pressure that's coming down on it. And you can measure the height of the column there and figure out the osmotic pressure. Now, as I mentioned before, reverse osmosis is when you apply a pressure that's greater than that osmotic pressure. And again, what that's essentially going to do is force all that water back across to the other side. And again, if you have a lot of really good filters kind of there by those membranes, you could filter out a lot of stuff that you really don't want, say, in your water. And again, that's sort of the process of reverse osmosis when you do that. Now, there are certain ways to describe solutions. They could be described as isotonic, hypotonic, or hypertonic solutions. And isotonic solutions have the same osmotic pressure as body fluids. And those are typically the IV solutions that they give you. And there are two solutions that are normally considered isotonic: 0.9% mass to volume sodium chloride solution, or a saline solution sometimes called, and a 5% glucose solution. These are what are considered isotonic solutions. And when you have an isotonic solution, if you take the classic example here, a red blood cell, and you slap it into a isotonic solution, because on the outside of the cell and the inside of the cell, the pressure is the same, what you will essentially get is equal flow in and out of that red blood cell. Remember, the red blood cell will act as a membrane, allowing things to flow in and out. But because the osmotic pressure is the same on both sides, you'll get that equal flow in and out of the cell. Now, if you have a hypotonic solution, hypo means less than. If you put that same red blood cell into a hypotonic solution, what that means is outside of the cell is less concentrated than inside the cell. And what's going to happen is osmosis is going to say, oh, all this water from outside needs to rush into the cell in an effort to dilute down the cell. And what that's going to cause the cell to do is start to swell and perhaps burst, which is probably not a great thing. And that is what is known as hemolysis. So because the outside is less than in terms of the osmotic pressure, inside is greater, you're going to have that flow from the solution outside into the inside of the cell, causing it to swell. Now, if you take a hypertonic solution and you put your red blood cell, hypertonic is greater than, and that means that outside of the cell is actually a higher concentration than inside the cell. So the cell's going to go, I need to dilute everything that's outside of me. And it's starting to give up all this sort of liquid and water. And what that's going to cause the cell to do is basically start to shrink. Also, probably not a great deal or thing to happen. And that is what is known as crenation. Hence why when you get an IV, they give you an isotonic solution, because probably if you're getting an IV, things aren't perhaps so great for you in terms of health. So you don't want to obviously give somebody a hypotonic solution or a hypertonic solution, which could cause their cells to start to swell and burst or shrink and go through crenation. So you want to kind of hydrate people, but still give them some type of solution that's not going to harm them. And so those two numbers, the 0.9% sodium chloride and the 5% glucose, is really important in terms of determining, what's going to happen in the cell. So here we have an isotonic solution on the left there, perfect donut. a hypertonic solution, donut hole, and a hypotonic solution at the end there. It swells up and bursts like a jelly donut there, and kind of a good way to remember that. So for example, if I put a red blood cell in a 5% sodium chloride solution, if I put a red blood cell in a 3% glucose solution, and if I put that red blood cell in just pure water, why don't you take a moment and think about what will happen in each of these cases. So just take a moment or two and think about, will nothing happen? Will it swell? Will it shrink? What should happen in each of these cases? All right, so let's take a look. So remember that isotonic solutions, the important numbers are 0.9% sodium chloride and 5% glucose, right? So if we put our red blood cell in a 5% sodium chloride solution, 5% is much higher than 0.9%. That means that this is going to be a hypertonic solution. And that means that this is going to happen here. The red blood cell, again, is going to be in a solution that is more concentrated. So the red blood cell is going to lose all its water and is going to start to shrink, right, and go through crenation. Now, if we put that same red blood cell in a 3% glucose, 5% is isotonic. So 3% is less than that, which means this would actually be a hypotonic solution, which is over here. That means, as we talked about, when the red blood cell is in there, outside the cell is less concentrated than inside. Everybody's going to rush in. And that's going to cause this guy to swell and probably burst. And again, that is known as hemolysis. And lastly, if we look at pure water, and that's sometimes a tricky question for a lot of people, people will sometimes go, oh, water can't hurt. But if you remember, we talked about pure water, and pure water has no osmotic pressure, which means, technically speaking, when you slap that red blood cell into pure water, the water on the outside is actually less concentrated than on the inside, and it's actually going to cause all the water to rush into the cell. So even though it's water and we sometimes think it can't be bad, it is actually not so great in this case. It is actually a hypotonic solution, and it will cause swelling and hemolysis to occur. Any questions on that there? And lastly, dialysis is a process that is similar to osmosis. It allows for small solute molecules and ions, as well as solvent water molecules to pass through, but it retains large particles like colloids. So here's a dialysis bag. Kind of works the same way. There's holes, again, allowing certain size molecules to pass through. Other ones get restricted. In our body, right, our kidneys and stuff do dialysis. They sort of filter out waste products for us that we don't want. So they act to sort of filter out those size molecules and certain molecules out of our body, while keeping, obviously, the stuff that we want still in there. So, in the body, dialysis sort of works that way, through our kidneys and stuff like that. And that is this chapter here. So that is chapter 10. And again, that will be on the exam 1 week from today, which will cover all of chapter 9 and all of chapter 10. Any questions on anything that we talked about? Okay, so I appreciate you guys coming back and hanging out even after this whole crash that we had. So that's it in terms of lecturing. If you do have questions on any of the lab and stuff like that, I know it may be annoying, but what I'm going to do is I'm actually going to stop this meeting. That way I have less sort of editing that I have to do for this, so I could just kind of put it up there. And I'm going to restart this meeting one more time. And again, if you do have questions, please come back through the lab link and I'll be happy to answer those. But just to save me some time, I'm not having to kind of edit out everything after this point in the video, which may not be of concern to anybody else. I'm just going to stop this meeting and then give me about a couple of minutes and then I will restart it if you do have questions. If you don't have questions or anything like that, then have a good weekend and all that good stuff, and I'll see you next week. So again, I'm going to stop this meeting and I'll restart it in a couple of minutes. If you do have questions, please feel free to come back.